Hello, everyone. We are Group 16, and our project is the High Accuracy Autonomous Interceptor Drone, also known as H.A.I.D. For this group, our project members are Saul Poveda, Natalie Roberts, Megan Latayan, Dylan Lima, and Kenzie Pierre. Our advisor is Dr. Shen Ni, and this is for Florida Atlantic University, spring 2025.
Hello, I'm Saul Poveda, and this is our project summary. As aerial technology continues to advance, there's an ever-growing need for autonomous systems that can respond quickly and effectively in the name of defense. The purpose of our project is to design a drone that can detect, track, and intercept a moving target without human input. We plan to achieve this by combining data from an onboard global shutter camera as well as other sensors, and then processing that information to guide the drone's flight controller. The fusion of this vision and sensor data allows the drone to make precise decisions in real time, ensuring reliable guidance and control.
Hi, my name is Natalie, and I will be talking about the software side of our proposed solution. On this slide, we're showing the overall solution for our Interceptor drone. My teammates will go over the hardware in more detail. But at a high level, our approach is to make the drone capable of autonomous path planning and interception, so it can compute its own route to the target initially. And then on board, it will support real-time target detection using QR codes and course correction to change the initial path so that the drone can update as the target moves if it is not on the initial trajectory path. On top of that, we will have a secure command and telemetry communications between the drone and the ground, aka us. Also, the ground station interface for monitoring mission status and allowing a human to take over manual control when needed because of the FAA regulations. For the software itself, I broke it into four main pieces. First, there's the trajectory planner. This part takes the drone's starting position and an estimate of the target's position and generates an initial interception path made of waypoints. Those waypoints are what the flight controller will follow in autonomous mode. Then there's the AI tracking and prediction. This module processes sensor data from the vision system to detect and track the target, and it will eventually predict where the target is going to be in the near future. And then we have the course correction logic that uses those predictions to update the path in real time instead of just flying a fixed route. Finally, we have the ground control interface, which displays information like GPS, battery, and target lock to the operator and supports manual override through FPV and controller. Together, these software components turn the drone from a remote-controlled aircraft into an intelligent interceptor.
All right, so my name is Megan Latayan. I'm an electrical engineering major, and I will now go into the hardware portion of the proposed solution with a brief overview of each of the specific subsystems. So starting with camera and imaging, it captures high-speed grayscale video and sends frames to the Raspberry Pi for AI detection and tracking. It also provides stable motion imagery feedback, which is crucial in identifying and locking onto fast-moving targets. Next is the propulsion motor control. This generates thrust and executes drone maneuvers using 4 brushless motors and a 4-in-1 electronic speed controller. This specific ESC regulates motor speed for stabilization, braking, and directional changes required during drone flight and attack. Moving on to the first-person view system, or FPV. This provides real-time manual control video feed for testing, emergency override, and safety supervision during autonomous flights. It incorporates the RunCam Phoenix 2 Nano first-person view camera, video transmitter, and operation goggles. We have the computing and processing subsystem, which runs computer vision, AI detection, trajectory logic, and communicates with the flight controller via Mavlink and ROS2. This also serves as the drone's onboard brain for perception and autonomous decision-making. Continuing with the last three subsystems, we have communication and control, which uses an express LRS radio system for manual pilot input and to control the signal redundancy. This transmits telemetry like the system state, battery, and GPS, and allows switching between manual and autonomous control. It also ensures reliable communication between all systems, meaning the drone, ground station, and the operator. The flight control manages signals from the electronic speed controller and stabilization of the drone, while the integrated inertial measurement unit provides a smooth flight. The navigation sensors primarily support autonomous waypoint following, telemetry, and positioning. And for the last subsystem, we have the power system, which delivers high current and is the main voltage source for motors and electronics. The integrated power distribution board regulates the voltage being transmitted from the battery to the Raspberry Pi 5, flight controller, sensors, and FPV gear. It also ensures stable and noise-free power during maneuvers.
Hello, everyone. My name is Dylan Lima. I am the computer engineer for this project. And now I'm going to explain to you how the H.A.A.I.D drone actually coordinates its autonomous interception. Our system is built from three major software pillars. ROS2 is for the ground control. RG-Pilot is on the actual drone, and our onboard AI perception stack. Together, these three systems allow the drone to see, think, and react in real time. First, ROS2 runs on our ground control station. Its main job is mission planning. This includes determining the interception route, predicting the target movement, and generating updated trajectories as the target changes direction. ROS2 consistently communicates with the drone using Mavlink, sending high-level commands such as the headings, the velocities, and waypoint updates for our Interceptor drone. It also includes a status monitor, which allows the information to be collected, such as battery health, GPS quality, and other error messages that are important to our flight. So overall, ROS2 acts like the mission commander. It's supervising the big picture and sending instructions while monitoring the drone's condition. For RG-Pilot, which sits on the flight controller inside the drone, this system handles all low-level control, meaning the drone's stabilization, it manages its attitude, it balances the motor, and it's keeping the drone flying safely. RG-Pilot receives high-level instructions from ROS2, such as the desired direction or the speed, and then converts these commands into actual motor outputs by controlling the ESCs and its motors. So while ROS2 decides what the drone should do, RG-Pilot decides how the drone physically performs. These separation keeps navigation smooth, stable, and extremely responsive during fast interception. Finally, we have our onboard AI perception. This is running either in flight or in gazebo simulations. We use a high-speed global shutter camera to capture a clean, distortion-free frames, which is very important during these fast motion interceptions. Those images are processed by our onboard AI to detect and track target in real time. Based on what the camera sees, our perception module predicts the target's motion and updates the drone's planned interception path. This creates a real-time feedback loop of what the camera sees, the AI, and then interprets it, then planner adjusts it. And then the updated command is sent back to ROS2 through RG-Pilot, which then loops continues again. This is what gives H.A.A.I.D its high accuracy tracking and interception in moving objects. So overall, these three systems, ROS2, RG-Pilot, and our perception pipeline, work together to create a drone that can sense its environment, make decisions, and execute precise maneuvers autonomously. For my subsystem, I am responsible for the flight controller and motor control systems. This is part of the drone, is what actually turns the high-level commands like direction, speed, or altitude into precise motor outputs that keep the drone stable and allow it to perform fast interception maneuvers. The overall objective is to design and implement a flight controller system that can reliably convert high-level instructions into the motor using the flight controller, the ESCs, and other onboard sensors. For our components, we are using the Squire FPV flight controller stack, which is a built-in 4-in-1, which has the ESC on top of the flight controller. This single stack gives us both the flight controller and the motors for the ESC in one compact unit, reducing wiring and improving reliability. It also reduces the amount of space that is being taken up in the drone to make a lighter drone as well. We paired this with the Xing E Pro 2207 motors, which are known for strong thrust, fast response, and stable performances at high speeds, something that is extremely important for us. We chose these FC stack because it can handle the high current of our 6-cell power system, which is necessary for the power levels of our drone cars. The 2207 motors complement this by providing the high efficiency and strong acceleration. Together, this setup gives us a reliable and responsive propulsion system that can keep up with fast-moving targets. The flight controller receives high-level commands from ROS2 through the MAVLink. It then translates these commands into motor signals, which sends into the ESC, which then finally sends to the motors. The FC also shares important sensor data and status information with the AI perception system and the power system, creating a complete feedback loop for safe and stable flight. If any of these information could be of error, it will go back to the ground control station and we can reset there. Some challenges we are working through include the motor tuning, understanding sensor behavior, and ensuring clean communication between the subsystems. For our early prototype, we've begun bench testing the flight controller, verifying the ESC's functionality, and checking the IMU sensor readings and performing basic motor spin tests. These steps help us confirm the system works properly before moving into full assembly and flight testing. Overall, the subsystem is what allows the drone to physically respond to the commands with accuracy and stability, making it a critical part of the H.A.I.D interception system.
Now I will focus on the initial trajectory path planning, which is the first major part Saul and I have been working on. The goal of this subsystem is to answer the basic question: given where the drone is and how the target is moving, where and when can the drone meet the target, if possible? We are currently using the initial position of the drone, the target's position, and the target's velocity as inputs. The path planner computes the intercept point and an intercept time, and then generates a sequence of waypoints between the start and the intercept point. Those waypoints form a simple, feasible path that the drone can follow. The idea gives us a good starting trajectory before the course correction logic begins to refine in real time. Furthermore, this is an intercept problem in a three-dimensional space. We are assuming that the drone can fly at a known speed, and we know the direction and speed of the target, meaning we know the velocity. Then we set it up as an equation that says at some future time t, the drone's position based on its speed should equal the target's position based on its current position and velocity. When you work that out, it becomes a quadratic equation in t. If the quadratic has a positive real solution, that gives us a valid intercept time. From that time, we calculate the intercept position, and then we generate waypoints along the starting line from the drone start to that point, dividing it into segments that the controller can follow. We have implemented this first in Python using basic vector math to compute the intercept and the waypoints, then recreated it using the same logic both in MATLAB and a Simulink model so we can eventually generate C++ code. The Simulink model currently runs correctly, but some of the function blocks we started with don't convert nicely into C++. So Saul and I are actively working on replacing those blocks so that they are compatible with code generation. The plan is to turn this into a ROS2 node that outputs waypoints to the rest of the system.
Next up, we have our target tracking subsystem. For target tracking, we're going to use a global shutter camera, which is a camera that is going to essentially capture a whole image frame at once. So it's not going to have any distortion that a normal camera would have. And that's going to be really important, especially when we're attempting to track a moving target. We don't want any distortion to maybe miscalculate how big a target is or where exactly it's going. And the camera data is going to be sent to the onboard Raspberry Pi. Specifically, we're going to be using the Raspberry Pi 5, which is basically going to be the onboard computer, the onboard CPU. And it's going to be running the onboard computer vision algorithms for object detection and tracking. And it's going to communicate with the flight controller through Mavlink. As far as identifying our target, we're going to use more of an unconventional method. We're going to be using objects marked with QR codes. And essentially, each QR code is going to encode like a unique ID, which is going to make it easier to recognize and differentiate between different targets. As far as tracking goes, what we're going to be using is the Kalman filtering model. And what that is going to do is it's going to predict target motion between frames. It's going to smooth out noisy measurements, and it's going to help maintain a lock. Finally, the flight controller is going to receive guidance commands via Mavlink. It integrates this information with its own sensor data and translates it into motor control for interception. And of course, there are going to be a few challenges. And a lot of it really has to do with the camera, including lighting conditions, motion blur, camera resolution. So with a lot of that, we're going to have to basically tweak the onboard global shutter camera settings, make sure it has a proper resolution, a good refresh rate, etc. But by combining the shutter camera and the Raspberry Pi's onboard processing, we're going to be able to create a pipeline for tracking and intercepting moving targets.
The last piece I will talk about is course correction, which has not been implemented yet. The initial trajectory assumes that the target keeps moving in a simple way, but in reality, the target can speed up, slow down, or change direction at any point. The course correction subsystem is meant to handle those changes. Our plan is to develop an AI-based model that takes the target's recent position and velocities from the vision system and predicts where the target will be shortly in the future. Based on this prediction, the course correction logic will update the drone's trajectory and waypoints in real time so that the interceptor can stay on an efficient path instead of chasing where the target used to be. We plan to connect this module to our vision system on one side and to the trajectory planner and flight controller through Mavlink on the other side. The main challenges we expect are dealing with noisy or delayed sensor data and making sure that these updates are stable and safe. Our plan is to prototype this behavior in simulation first using Python and ROS2 with Gazebo and ArduPilot, and then moving it into the real world once it works in the simulation environment.
This is our wireless communication subsystem. And the way that we're going to handle wireless communication is going to come from two main technologies, including ELRS or Express LRS and the Mavlink protocol. So ELRS is the low latency radio link between essentially the pilot's controller and the drone itself. What it's going to do is it's going to let us override the drone flying autonomously just in case anything happens, and it's going to let us pilot the control inputs ourselves. So essentially, it's going to give us a safety net to make sure that we keep the control link active and stable, just in case we need to manually override the control. And as you can see on the right-hand side here, we have our FPV flight controller, which is basically going to be responsible for handling all the data we get from, for example, our camera, our sensors. And it's essentially going to use Mavlink, which is the protocol, very popular protocol used for mini drones. It's going to handle telemetry like GPS, battery life left, altitude, and other sensor data. And it's essentially going to let us control the exchange of data between different subsystems, for example, between the Raspberry Pi and the flight controller. And it essentially is going to let the Pi send navigation commands and receive status updates, etc. So it's really the language that's going to tie the autonomous side of the system together. And when we combine both ELRS and Mavlink, overall, it's going to support telemetry. It's going to let us manually override the system. It's going to let us communicate with and take in component data and the exchange of data. So it just keeps things overall reliable and flexible. But overall, the two biggest challenges that we're going to have to encounter is ELRS interference. Since it is a radio signal, we want to make sure that we keep that bandwidth strong, especially in noisy environments. Additionally, Mavlink has limited bandwidth, and of course, we have a lot of signals coming in and sensor data coming in, so we have to prioritize the most important data that we need. But even with those limitations, these two systems are really the backbone of how our drone is going to communicate and stay under control.
All right, now we're going to get into the vision subsystems. So this provides both low latency analog video for manual control and safety and digital imaging for the AI processing. This is configured primarily from a 2-camera design, which will ensure that the drone can operate autonomously while still allowing the operator full visual awareness and control. The two types of cameras that we'll be using are a global shutter camera, which is a digital camera, and an FPV, which is an analog camera. So for the global shutter camera, it captures high-speed, distortion-free frames with system communication for fast digital capturing, while the FPV camera provides live, minimal delay pilot view for manual override, takeoff, landing, and emergency safety. In figure 5 below, we have an actual photo from the global shutter camera, which is just showing us holding a soccer ball into the view of the camera from the Raspberry Pi feed. Now, getting into each of the specific components in the vision systems, we have obviously the global shutter camera, which produces stable imaging for AI tracking, eliminates rolling shutter distortion at high speeds, stable object detection due to fast frame pipeline, and it has an AI integration with Raspberry Pi. As for the FPV camera, it is a dedicated manual flight camera that is independent from the AI pipeline and ensures stable visibility during override. Now, the main microprocessor, which is the Raspberry Pi 5, is an onboard processing hub for AI and vision. It runs detection and tracking, and it interfaces with the flight controller and Mavlink. The last kind of components that we have are the visual transmitter, or the VTX, and the FPV goggles. These allow for real-time analog transmission and receiving, minimal latency, and the pilot receiving smooth, uninterrupted feed. Now let's further explore the different interfaces and challenges with the vision subsystem. So the first interface is with the software side of things. So this sends the camera frames to AI detection and tracking. The AI outputs target coordinates that are shared to the path planning subsystem, and it sends target lock and loss to the ground control interface. Well, the interface with the hardware consists of the Raspberry Pi 5, which communicates with the flight controller via UART and Mavlink, and the FPV camera connects to the VTX for manual flight control, while both cameras are mounted on the drone nose to maintain a full range view. Some of the known challenges are the lighting changes that could affect the detection of the drone, the vibration distorting image clarity, and the Raspberry Pi 5 processing and overheating with the load. As for the unknown challenges, there's the real-world latency from the cameras to the Raspberry Pi and flight controller, the outdoor sun/glare that could cause an effect on the performance, and the integration timing between vision and path planning. And lastly, for the vision subsystem, we have the early prototype implementation. So as far as the things that we've actually implemented already, it consists of the global shutter cameras successfully connecting to the Raspberry Pi 5 and producing live feed, as well as the pre-processing working and object detection. And we also have the FPV camera and goggles tested and stable. Now, for future implementation, we still need to finalize and integrate AI tracking with the Coral accelerator and the Mavlink waypoint updates. Now, moving on to the communication and control links, this subsystem enables reliable command, telemetry, and manual override by linking the flight controller, Raspberry Pi 5, ELRS system, GPS module, and FPV system to the ground control interface. And through this, the system ensures drone can seamlessly switch between autonomous and manual control. And the flight controller can transmit telemetry, meaning like the battery and GPS signals, to the Raspberry Pi 5 and the ground interface, while the ELRS radio link ensures low latency manual control signals from the transmitter to the drone. And the FPV goggles can provide separate analog video feed to support safe manual override. As far as the specific components, we have the ELRS transmitter and receiver, which is for the reliable RF link for manual override, supporting telemetry, signal strength, GPS, and battery, and it provides long-range, low-latency control. The GPS and compass module is essential for mission state display and mapping. It provides location and heading and interfaces with the flight controller. And speaking of the flight controller, the telemetry output sends battery, attitude, and GPS and failsafe data. It communicates to the Raspberry Pi 5 over Mavlink and acts as the bridge between sensors and ground interface. And lastly, we have the Raspberry Pi 5 and FPV goggles. This routes telemetry from the flight controller to the ground interface, ensures visibility if autonomous functions fail, and sends mission state updates. As far as the interfaces and challenges, we have two main interfaces with the communication and control links, which are the AI and vision system and the power system. So for the AI and vision system, we have AI lock being sent from the Raspberry Pi 5 to the ground control interface operator. The vision status, which is the lock or no lock, is sent to the mission state reporting. And a key thing to remember is that the AI decisions do not override ELRS manual control. Now for the interface with the power system, the battery voltage is reported through the flight controller, and the ground control interface displays battery health for safety. A few of the known challenges are the RF interface between the ELRS and Wi-Fi signals, maintaining reliable GPS lock in testing areas, and correctly routing of telemetry to avoid data loss. And some of the unknown challenges consist of the GPS multipath errors depending on test environments, real-world noise affecting RF performance, and any potential need for filtering to suppress electronic interference. And lastly, I'll discuss the early prototype implementation for communication and control link. So as far as the things that we have implemented, we've done the ELRS transmitter and receiver being fully paired and bench tested on our tester drone that we've built. And we have the Mavlink telemetry confirmed between flight controller and path planning. But for our future implementations, we still need the Mavlink telemetry to be confirmed between the flight controller and the Raspberry Pi, as well as the GPS module recognizing the flight controller and coordinates displayed on the ground control interface, and manual override priority verification during flight tests.
For this subsystem, I am responsible for designing and implementing the testing and validation procedures that make sure the H.A.A.I.D drone performs safely, accurately, and reliably. Our testing strategy uses both simulation environments and real-world flight tests to validate the interception, the stability of the drone, and the system behavior. Why we test in both simulation and reality? Well, because we start in simulation because it allows us to test our interception logic, our sensors modeling, and tuning without risking any hardware and allowing us to lose money on our project. Once the system is stable and the prediction in simulation is true, we move to physical tests to confirm that the drone behaves the same way in the real-world conditions. In simulation, we use Gazebo to run interception scenarios, measuring its accuracy, response time, and how well the drone tracks the target's movement. We also test our AI perception pipeline to make sure the detection and tracking performs correctly under different conditions. Simulation is where we tune control gains, adjust mission logics, and test edge casings like sudden target turns or fast acceleration. Because simulation gives us zero hardware risk, the stage builds confidence before we even arm a real motor. After simulation results meets our criteria, we move into a controlled field testing with the real drone. Here we verify that the drone can safely detect, track, and intercept a target in real time. During physical testing, we measure stability, battery behavior, link quality, and false safe responses, things that can't be perfectly modeled in simulation. We also compare real-world flight logs against the simulation to check for results that may not be consistent or reliable or that repeat too often to make sure everything is correct. Some challenges that we face include matching simulation behavior to the real world, accurately having the sensors be modeled correctly, and designing safe tests that avoid harm or damage or completely destroying the drone. Right now, our early prototype has basic interception scenarios running a simulation, and we've already defined the key performance metrics, and we'll be tracking during the full flight testing once we get to that stage. These testing procedures ensure that every part of H.A.I.D, from perception to motor control, meets our safety and reliability requirements before the final deployment.
Hello, my name is Kenzie Pierre, and I'll be talking about the slide called Power and Propulsion System. Now I'll explain the power and propulsion system, which is one of the core elements of the H.A.I.D system. Everything begins with a 6-cell LiP battery, which is responsible for supplying power for every single component of the drone, from motors to Raspberry Pi to the FPV system. Because our drone requires high current for rapid acceleration and interception, this battery gives us the necessary voltage and discharge rating to support high-speed maneuvers. Next, we use a BEC, or battery elimination circuit. This gives us more than 22 volts, the battery gives us more than 22 volts, which is too high for components like the flight controller and Raspberry Pi. The BEC protects these sensible electronics by stepping the voltage down in stable 5 or 6 volts. Without the BEC, we risk burnout or damaging the computer system mid-flight. Then we have the power distribution board, or the PDB. The PDB acts like the electrical hub of the drone. It takes the raw battery voltage and distributes cleaning across the subsystems, including the ECS, flight controller, camera, sensors. Now is the brushless motors. These motors, powerful, lightweight, and effective, allow the drone to generate strong thrust completely. In interceptor scenarios, this burst acceleration is crucial. The ESC regulates how fast these motors spin and enables precise maneuvering. Finding the propellers converts motor rotation into actual lift, allowing the drone to fly. Thank you. Project schedule and timeline, the software side. We're splitting this up into the fall semester and the spring semester. In the fall semester, September, they outline the core project specifications. This includes identifying features, constraints, and initial system responsibilities. In October, the team begins researching components and must integrate with software framework like RSID, Gazebo, and Arduino. November is when we create our own system block diagram, building the foundation of how software models communicate with hardware. By December, the software team continues deep research to solidify the entire architecture. The spring 2026. In January, the team steps up the full software environment, like ROS2, Autopilot, and Gazebo, and MATLAB communication layers. By February, the initial tracking module is developed, meaning the AI begins detecting moving objects in simulation. In March, trajectory path planning and MathLeak integration are implementing, allowing the drone to receive and follow anonymous waypoints. During April, the course correction model is added. The hardware in the loop test begins, meaning the simulation starts interacting with real components. By May, the team aims to work fully system building the simulation and real-life testing. Thank you. For the slide, project schedule and timeline, the hardware side. In fall 2025, in September, we outline hardware requirements. This includes the motion selective camera specifications and identifying what components must support anonymous flight. In October, we create block diagrams that map out each hardware system, connects electrical and mechanical. By November, we complete the research of all the drone components, motors, the ESC cameras, GPS, radio system, and the Raspberry Pi. In December, we place orders for all parts so we can begin the next semester. In spring 2026, January, we begin learning SolidWorks so we can design a custom drone frame and fit our interior electrical tower and systems. In February, we start creating and refining the new drain brace model, making sure all components fit and allow the airflow, vibration control, and balance considered. By March, we begin physically adding components to the design drone. This includes monitoring the motors, wiring the PDB, installing the PI, and the GPS and flight controller. In April, we begin to test flight with a fully assembled model, initiating manual and later with partial autonomy. Finally, in May, the team aims to complete a hardware system working and ready to fully integrate and demonstrate. Thank you very much. List of tasks for computer science and computer engineers. First, we have Natalie, our computer science team member. She designs and implements trajectory path planning algorithms. She also develops prediction algorithms that help the drone adjust its course in real time. Natalie works closely on ROS2, node development, and helps configure the simulation environment. She collaborates with SAW to integrate AI tracking, resulting into the navigation decisions. Next, we have SAW, also from computer science. SAW designs the AI systems responsible for object detection, tracking, and trajectory prediction. He develops real-time computer vision using ROS2 and Python/C++. SAW integrates all AI inputs into flight planning and planning system and manages MAVLink communication routes. He also ensures the AI model works smoothly with the other subsystems. Finally, we have Dylan, who is our computer engineer. Dylan designs, implements the flight controller, which includes the ECS, motor management, and on-by sensors. He verifies that the hardware being used in simulation matches what he will use in real life. A key part of his role is serving as a bridge between hardware and software teams to ensure system compatibility. He also assists with selecting components that support the AI and flight controller requirements. Thank you. Finally, we have the last list of tasks, the electrical engineers. Starting with Megan. Megan designs and implements the visual system, which includes both global shutter digital camera and the FPO analog camera. She leads all imagining hardware integration, everything from mounting the sensors to wiring and testing them. Megan plays a major role in drone's mechanical layout, particularly stacking the interelectronics. She also works closely to ensure vibration, isolation, and wiring cleanliness and hardware stability. Now for my role, Kinsey Pierre. I design and implement the power and propulsion system, which includes the battery that we have, the BEC, the PDP, the ESC, motors, and propellers. I assist in researching and testing all components to ensure that they all meet performance requirements. A major part of my responsibility is participating in the physical construction of the drone, including wiring, soldering, integration of all power components. I perform voltage, current, and power distribution testing to ensure that the system remains safe and stable during high-demand flight operations. Together, Megan and I build the electrical and mechanical foundation of the drone, ensuring it can fly safely, deliver power reliably, and support all the software systems the rest of the team is developing. Thank you.